Welcome everyone to the latest Earthmover webinar. This topic is one that is really interesting to me and evidently to a lot of you. This is the most attendees we've ever had sign up for one of these. So really excited to share what we've been learning. I know there are some folks in the room who are very experienced on this topic and others who are very new to it. But in any case, let's dive in. Just a little bit of housekeeping and logistics. There's a lot of people on the call, so we're going to, feel free to use the chat to ask questions, and we'll have a structured Q&A at the end of the hour. Okay, so yeah, with that, let's dive into it. So our topic today is running AI weather forecasts in the cloud with ECMWF's AIFS model, AWS, Coiled, and Earthmover. Okay, so just to make things fun and get started with a fun visual, here is a video of the forecast I generated myself just yesterday using AIFS. And so we're looking at temperature, shortwave radiation, total column water vapor, and precipitation, right? And so this is the type of forecast that we're going to learn how to run. I love looking at these images. I could look at them all day. They're quite beautiful. They're also incredibly useful for a wide range of different purposes. So presumably this is why you're here, because you're interested in this. So a little bit about myself. I am Ryan Abernathy. I am the CEO and co-founder of Earthmover. My background is as a climate scientist and oceanographer. So I spent a decade as a professor here in New York at Columbia University, really doing a lot of high-resolution Earth system modeling. And so this is a really interesting topic for me to run some models and think about their performance and how to optimize them in a cloud context. And of course, I spent a lot of time also in the Pangeo community as a contributor to a wide range of different open source tools, and you'll see many of those showcased today. A little bit about our company, Earthmover. We are a public benefit corporation, and our mission is to empower people to use scientific data to solve humanity's greatest challenges. And certainly climate change and all the risk that brings is near the top of that list. So our team is made up of accomplished scientists, open source community leaders, and seasoned engineers who have worked at some of the top tech companies in the world building production grade infrastructure. So we're thrilled to be building the cloud native scientific data platform of the future. And AI weather forecasting is a fantastic application, a great fit for the platform that we have been building. So excited to show this for you. We're really proud of the leadership role we play in the open source community. We are a leading driver of the X-Array package. We employ many X-Array developers at the company and are really helping set the roadmap for that very impactful data analysis tool. We help run the ZAR project, which is a really powerful storage format for tensor and array-based data, especially in a cloud context. And you'll find many of the popular AI weather forecast data sets distributed in ZAR, such as WeatherBench. And then more recently, we released Icechunk, a transactional storage engine for ZAR, which brings some really powerful benefits such as ACID transactions and performance improvements on top of ZAR. And we'll be highlighting Icechunk in this talk quite a bit. It has an important role to play here. The platform that we are building and providing to our customers looks a bit like this. So our platform goes beyond just the open source software and offers a fully managed data platform for scientific data. It runs on all the major clouds, Google, AWS, and Azure. And it has two main layers. At the base is Arraylake, a data management layer that provides data catalog and data governance capabilities, all using the open source Icechunk format on disk. And then on top of that, we have a new product called Flux, which is a API gateway that serves up various geospatial APIs from your data allowing you to easily connect the data stored in Arraylake to GIS applications, web maps, databases, et cetera. So I'll highlight Flux a little bit at the end of the talk. So this platform is really ideally suited for AI and ML workloads, from ingestion to processing and feature engineering to training and inference, and finally to data delivery. All of these aspects of the AI ML workflow depend on really performant cloud-native data access, and that's precisely what our platform provides. So I'll be highlighting specifically the advantages here for inference and data delivery. And of course, we're proud to have some of the leading institutions and innovators in this space as customers using this platform day to day in their groundbreaking work on AI-based Earth system modeling. So here's a very dry-looking slide, which is an outline of the talk I'm going to be giving today. And I just wrote it mostly to help organize myself. But I'm going to start by, giving an overview of AI weather forecasting. What is the technology? What are the use cases? And explain specifically some details about AIFS and why we chose to work with that model here. I'm going to talk about the workflows involved in AI weather forecasting, specifically training and inference. And we'll look at an example inference pipeline that ECMWF distributed and try and understand some of the performance implications for how that notebook runs. Then we'll introduce an optimized inference setup using a cloud-native data infrastructure. That's going to feature our platform, and it's also going to use Coiled as a way to help orchestrate compute. We're going to walk through the code that is used in these pipelines for both ETL and inference, and discuss some of the key optimizations we made that were able to reduce costs from our initial starting point by almost 90%. Then finally, we'll sort of show the icing on the cake. We'll show our Flux application running on top of this data, querying the data we just produced with our forecasts. Okay, so let's dive into it. So starting point, I think, let's think about how conventional weather forecasting works. So conventional weather forecasting, the sort that all of the major national weather forecasting agencies do, is fundamentally based on data assimilation, process in which a wide range of different observations of the atmosphere and Earth system are incorporated and integrated with a physical model, ultimately a model that's solving partial differential equations and modeling the atmosphere. And that process is computationally expensive and typically runs on a big supercomputer. And this infrastructure is used to produce an analysis, a forecast, and often a reanalysis. And so this is the sort of status quo and the way we've been operating with weather forecasts for decades. And it is fantastic. It has served society very well. And it's going to be with us for a long time going forward. This is not going away. However, AI is complementing and providing new opportunities to explore weather forecasts in new ways. Just to give some basic overview for folks who are new to this topic of how forecasts work. Basically, observations are brought in as quickly as possible from the field, from satellites and sounders and all of these instruments, used to produce a best guess estimate of the current state of the atmosphere. That's called an analysis. And then that analysis is run forward by this data assimilating model to produce a forecast. And this process is repeated over and over at different timescales constantly. And this is what operational weather forecasting centers do, and how they produce the weather forecasts that power all of our, the apps in our phones, as well as much more critical decision-making systems like, at airports and stuff like that. Now, you've probably heard of AI weather forecasting if you're here. So there is a wide range of exciting new approaches to weather forecasting being pursued. And these have garnered a lot of attention in the media. So here is just a smattering of different AI weather forecast products that are available out there. We've got GraphCast and more recently GenCast from Google. We've got NVIDIA's Earth-2 project. Those are big tech companies. And then there's a bunch of really cool startups. Here I'm highlighting Salient, Silurian, Xcarta, Brightband, Jua, Zeus AI. These are all innovative startups who are producing new AI-driven weather forecasts. So I just want to make a disclaimer here. I'm not here to evaluate or weigh any one of these forecasts against one another. I'm not an expert in forecast model evaluation. I just think it's great that we have all of these options and all of these choices. So how do these AI weather forecast models work, and how are they different from conventional weather models? Well, fundamentally, all of these models that I've described are based on some form of deep neural networks and use what we broadly call deep learning. There's a very wide range of architectures in use across the different models, and this is a super active topic of research. And so I'm not going to try and say, which is the best one and make any recommendations. What I'm showing here is a figure from the DeepMind Google research paper on GraphCast, which shows a pretty common architecture that's become quite popular and is in fact similar to what's used in AIFS, which is called an encoder processor decoder architecture. So the input state is encoded into a latent representation. Processing happens in that layer, and then it's decoded back out to more of the physical space representation. There's also a lot of work happening with foundation models, for example, Microsoft's Aurora model. One thing a lot of these models have in common is that they're typically trained on reanalysis data. And this is important to keep in mind, just because that reanalysis data is itself produced by the sort of conventional data assimilation process. And so these AI weather forecasts aren't truly independent of the conventional weather forecasts, and you might think of them as a form of emulator of those forecast models. The asterisk here is to say that there are certainly plenty of teams who are pushing that forward and building more data-driven weather forecast models. But with the one I'm going to show today, it's definitely the case that it's trained on reanalysis. These models can have skill that's equal or better than conventional models. And the really exciting thing is that the process of running inference, making a forecast, can happen on a single GPU or a single compute node. And that is what is, in my opinion, so transformative about this technology for a lot of end users. The fact that the forecasts are so cheap to run means that the ability to run weather forecasts is becoming democratized. So whereas for conventional forecasting, you basically need a specialized multi-million-dollar supercomputer to run the forecast, these AI forecasts can run on a single GPU in a matter of seconds. So there's a lot of exciting use cases for AI weather forecasting, and I won't possibly highlight them all, and I'd love to hear from some of you of what your use cases are. But certainly energy trading is one of the ones we hear about a lot. Being able to predict supply and demand with tailored weather forecasts enables traders to make better decisions and ultimately save or make money. Logistics and supply chain is very sensitive to weather, so understanding how weather impacts the supply chains can help them optimize. Insurers are very interested in modeling risk and extreme events, and so these AI weather forecast models have big implications there. And of course, for research, this is an incredible opportunity for us to just understand the Earth system better by having these extremely fast ways to simulate the Earth system. It opens up all kinds of interesting research possibilities. And there's dozens of others, but these are just a few worth highlighting. Okay, so let's talk about AIFS and why we chose to use AIFS for this demo. So AIFS is a model that is developed and distributed by the European Center for Medium Range Weather Forecasting, and I want to just acknowledge the fantastic work that they do. I see some folks from ECMWF here, and we're thrilled to be able to use this for the demo. I would say that the AIFS architecture is somewhat inspired by GraphCast. It's an encoder, processor, decoder architecture with plenty of customizations and optimizations and innovations that have been made by the ECMWF team. Fundamentally, it produces and consumes data from the ERA5 N320 Gaussian grid with approximately 31 kilometer spatial resolution. In the words of the paper authors, AIFS represents a step change in forecast skill compared to IFS, the conventional ECMWF forecast model, achieving up to 10% better scores. And so over here, you can see a plot of the RMS error for surface temperature between AIFS in blue and IFS in red. And so across the board at all forecast times, it's producing lower error compared to observations than the conventional model. So not only is it faster in many measurable ways, it is better. Not all the metrics are so unambiguous. And of course, as a disclaimer, you should always evaluate these forecasts carefully for the specific metric and purpose that you're interested in. But overall, this is pretty exciting. Now, beyond just the skill, there's some really important characteristics of AIFS that I want to highlight. For one, it's an open source model, so you can go get the source code and run it yourself. And even more crucially, the weights of this model, the pre-trained weights that ECMWF has produced, are also open source, licensed under a Creative Commons attribution license. Now, this is key. If you're aware of some of the other models in this space, the code is open source, but the weights are only licensed under a non-commercial license. And so that prevents commercial organizations such as, for example, Earthmover, or probably many of you, from using those weights in a commercial context. And AIFS is instead much more open and liberally licensed to do whatever you want with, provided you provide attribution, which I am doing right now. Thanks, ECMWF. Beyond this, we've found the AIFS just has great documentation. It's a very user-friendly model. And we see this as part of this broader movement at ECMWF towards open science, involving other efforts such as EarthKit, Anemoy, et cetera, that is really, it's a really clear and effective effort to actually make these tools usable. And so we've taken full advantage of that here. Now, let's talk about some of the workflows with these AI weather models. Specifically, there's two main workflows involved in AI weather models. One is training. So this is where you are actually making the model learn from data, running the model forward, computing the loss function, and retuning all of the millions of weight parameters to make the model skillful. This is a very expensive process. It takes a lot of GPU time. But fortunately, this is already done by ECMWF, and they've released the weights, the results of their training. And so what we're going to be showing today is much more lightweight. This is inference, where we're taking those existing weights and rolling out the model in forward mode. And this allows us to run the weather forecast. So it's relatively cheap, but still not trivial. And it can be done, by anyone. And so this is what we're going to focus on today. However, I just want to note that many of the themes that I'm going to highlight around efficient transformation of data, pre-processing, and especially efficient loading of data from storage are just as relevant to model training as they are for inference. So I just want to have folks keep that in mind. If you are interested in training, I think many of these themes and concepts do carry over. Okay, so the starting point for our inference pipeline is a wonderful notebook that ECMWF has provided within the Hugging Face repository for AIFS. And so you can go have a look at that notebook. I'll run some of the code from it. And in fact, I'll just jump over to a notebook that I actually have running in another tab here and run some of this code. And so I'll just step through some of these cells. And a lot of what this code does is download data from ECMWF open data locations. So we're getting surface data, we're getting soil data, and we're getting pressure field data, pressure level data, all of the fields that are needed to initialize this model, right? The way these models work, they need to know the initial state, and then they can step that forward. And it's fantastic that we have all of this open data from ECMWF. They provide all of this freely, and they provide a great API for us to go access that data. However, as you can see, downloading this data does take time. In our tests, it's taken usually 2 to 3 minutes to download the initial conditions for a single forecast run. In this case, we're using the ECMWF open data on that are on AWS already. So we're already in the cloud. We're running everything in the cloud, yet still, because of the way this is architected, we're downloading grid files, opening those grid files. It's just not a very fast data loading experience. We'll come back to that. And so, some of the questions we had about this notebook were, what sort of environment and hardware do we need to run it? This has some pretty complex software dependencies, and it requires a certain type of GPU in order to work. How should we orchestrate an inference pipeline, right? So the scenario we have in mind is where we want to make a lot of weather forecasts, say reforecast an entire year in order to do custom analysis or some sort of custom research application. How should we store the results of those forecasts? So how should we save the outputs back out? And in particular, how should we optimize performance to minimize our GPU bill? Because in this notebook over here that's downloading data, I'm actually sitting on a fairly expensive GPU just waiting for data to download. So when we did a performance analysis of this original notebook that was running in AWS and feeding data from the ECMWF open data, we found that we're spending over 2 minutes downloading and reading grid files, while rolling out a 48-hour forecast only took us 10 seconds. We also observed that if we wanted to regrid the outputs of the model onto a lat-long grid in order to have them more accessible for analysis later, that was taking quite a bit of time as well, 20 seconds or more. And so, the main point here is that the time spent actually using the GPU in this inference scenario was just a small fraction of the total compute time for one of these tasks. And that is not an efficient use of resources. Again, I'm not criticizing anything about this notebook. I'm just identifying some options for how we can optimize it in a production context. So the cloud native data infrastructure that we have used in the demo that I'm going to share is, of course, based on AWS, but then uses 2 other services on top of AWS to make a much more user-friendly and convenient and sustainable, governable data infrastructure. So the first of these is Earthmover, our high-performance tensor data management platform. So we're using Earthmover to essentially store, optimize initial conditions, and also the results of our inference. And that is all happening on disk using object storage, using this optimized Icechunk format. We're also using Coiled, the company behind Dask, to provide user-friendly orchestration of all these cloud compute jobs. So Coiled is a friend company of ours, and they make it super easy to deploy compute jobs on CPU, GPU, and get clusters in the cloud. And so by using both of these tools, we're able to really simplify our infrastructure and just get this thing running really quickly and easily. A few words about Icechunk, because it's an important piece of this infrastructure. So Icechunk is what we're going to use to actually store our data on disk. And that's how we're going to take the 2 minutes data loading down to just 1 second. So Icechunk is a transactional cloud native storage engine for XAR. It was designed from the ground up for object storage, and it also provides ACID transactions to work more like a database. So we can safely write to these Icechunk stores and read from them with multiple readers all at the same time. Now, Icechunk is compatible with Xarray. It's very easy to integrate with PyTorch and TensorFlow. And the core is implemented in Rust with just a thin Python wrapper on top. It's 100% open source and licensed through an Apache 2.0 license. Here's some results from a pilot we did recently with NASA, just focused on the performance of extracting data from, in this case, existing netcdf files. So here, that's something I didn't mention, but in addition to storing ZAR data natively, Icechunk can actually virtualize over existing netcdf or GRIB or HDF files and really supercharge the speed at which we can read data from those files. So here was a query that we performed against some precipitation data from NASA. And this query was taking almost a minute with their on-prem infrastructure, and in the cloud, we made it run in just a few seconds. So Icechunk is a part of how we're going to be getting this really good I/O performance. So in the pipeline I'm going to share, there's two steps. As a first step, we run an extract, transform, load pipeline where we're taking data out of these GRIB files and transforming it into Icechunk format and storing that in the Earthmover platform. And so each of these tasks to read these initial conditions is relatively slow. You saw some of that in the notebook. But we can parallelize it heavily, and we can use cheap CPU spot instances. We don't need to be using any fancy GPUs for this. So this is just a data transformation job. And we're taking this data and we're storing it in our Arraylake platform. And so here I'm going to show you what Arraylake looks like. So this is, think of it as a database for this multidimensional data. Here we've got our home for the Earthmover public organization. We're managing data across 4 different cloud object storage buckets. And data are organized into repositories or repos. So you can think of these as like GitHub repos, except for ZAR data. So here are these AIFS initial conditions. So here we can see we've got initial conditions for, pretty recently. We could populate this even more recently if we wanted to. We can go zoom into one of these and look at some of these fields. And what we've got here is just the full initial condition data, all stored as one optimized tensor that we can just really quickly and easily load into memory. And so if I just pop back to this notebook, you can see here it took us 2 minutes to download the GRIB files. I'm going to now connect to Arraylake from this notebook. I've already logged in here, so I have access to this data. And in this cell, I'm just going to connect to the to Arraylake and load all of the data, both the current date data and the previous date data, or the previous 6-hour period data, and we can pull all of that data into our notebook in just 2 seconds. And so that is, so much faster than what was happening before. And so this is really going to save us time, having this data stored in this optimized way. And so those jobs have been run, and I'll share the code later that we use to run these transformations. Step 2 is inference. And so in our inference jobs, we're now taking that data that's been stored in this optimal way, and we can load the initial conditions super quickly. And then our inference job can just focus on rolling the model out. And then we're going to save the outputs of that also into back into the Earthmover platform as a result of our jobs. And this is also something we can scale out and parallelize over many different forecasts. Now, we have to use a relatively large GPU in order to run those inference jobs. And so we care a lot about the performance within that inference job being good, so that we don't waste money on GPUs that we're not using. And so here is some of the performance optimizations that we made in order to optimize for our GPU costs. So by far the biggest one is just the loading of the initial conditions. Moving from the open data API calls to the Icechunk backed store in Arraylake, we were able to reduce our data loading time from 2 minutes roughly down to 1 second. We also found some fun tricks, a way to do the regridding of the outputs on the GPU, since we're already sitting on a GPU on this node, and the regridding is based on just linear matrix multiplication. We moved that over to the GPU, and that allowed us to store regridded outputs without slowing down our inference jobs. Finally, and I'll show you when I walk through the code, we decided to interleave the output storage, writing the outputs in a separate I/O thread happening in parallel with the inference. And this allowed us to eliminate the overhead for writing. So rather than having to wait for us to write data, we sort of did this in parallel on the CPU while the GPU was running the inference. And so, you know, as a result of this, if we wanted to reforecast an entire year for 48 hours each forecast, you know, these optimizations take the cost from, okay. So this is the fun part. This is where we get to look at some code. So let's see. Get all these things going again. Okay, great. So let's go look at our code that we use to run these various pipelines. Okay, so this is, maybe someone can drop the link. Oh, have I not made this public? Okay, let's make this public right now. I'm just going to make this whole repo public. So let's see, manage visibility. I'm going to change visibility, change to public. Okay, great. So now this repo is public. So maybe someone from the team can share this link so other folks can crawl through it. So this is an open source. This is all licensed under Apache 2.0. Some of the code here is derived from ECMWF's original code and has been used under the terms of that license. So what we've got fundamentally here is a command line script that does two different things. We have an ingestion flow and then a forecast flow. And so the ingestion flow is what we use in order to populate our database of initial conditions, and we just specify a start date and an end date. And then we have a forecast flow where we do the same. We provide a range of different dates we want to do a forecast for, and it just goes and does it. And so I'm going to click through and highlight some of the key things. Let's start from the software environment. So we actually created two different software environments here to run in Coiled. One is the GPU-enabled environment. That's a pretty heavy-duty environment. And the other is a much more lightweight environment used just for the ETL. I just want to highlight that setting up this environment to actually work with AIFS was not super trivial. You need specific versions of PyTorch, Torch Vision, and you need this flash attention package. And so a lot of our time was actually spent trying to figure out how to get a proper Conda environment that AIFS would actually run in. And hopefully this is useful for folks who want to do the same. You can reuse the same environment. Now, as for the code itself, I'll just walk through some of the highlights here. Fundamentally, what we're doing here is we have a function that gets the data from ECMWF open data and stacks that into a single NumPy array and then stores that into a ZAR group. And so when we scale out our processing, we just run this function against a bunch of different a bunch of different initial conditions and store these as separate ZAR groups within one Icechunk store. And so I'll show you the ETL flow here. We have this ingestion flow. And the way we interact with Coiled and Dask is we create a Dask cluster, which is auto-scaling. And then we just submit a bunch of tasks to it to get and store the data for each forecast date. That runs, we collect the results back together, and then we commit a single Icechunk session at the end of all of that. The forecast pipeline looks quite similar, except we do it on a GPU cluster, and we found these G6E X large or 2X large instances work well for doing this forecast, and they're probably the most cost-effective option. And so we just submit these tasks to run a single forecast. And I'm going to show you what that forecast run looks like. So when we're running that forecast, looks like this. We load some initial conditions. That's the part that we optimize, and it takes just a second or two. We also set up a regritter, so we have a custom module that does regridding of the data on the GPU. We set up a queue to hold the results of our output, a multi-threading queue. And we define a worker process that just takes items off this queue, and whenever it finds one, stores them to ZAR. When we go into our main forecast loop, so here's our main forecast loop, we turn our state of each forecast into an X-array data set, and then we just put this into the queue to be stored. And at the end of the forecast loop, we join the queue and make sure all those tasks have finished. And this is how we are able to have the model running and have the storage and I/O happening on the back end. And so here is a DAS cluster where you can see we've done a bunch of these forecast runs, and you can see these are running generally. Each forecast, 48-hour forecast, is running in less than 30 seconds end to end for the full task. And so during that time, the GPU is most fully used the whole time. Okay, and now finally, I want to show the outputs of those forecasts, which, they're in another organization here, Earthmover Republic. We're storing those in a repo called AIFS outputs, where we have a group for each forecast, and we can go in and have a look at those. And so here we can see one of our forecasts, and these are now stored as a sort of more standard X-array style data cube where we can easily load and plot and query them. And so I'm just going to pull up another notebook that is running here, where I'm going to open up one of those forecasts, and we can just have a look at that in X-array using our favorite tools. So here's a total precipitation from one of those forecasts. We can easily pull up, make a plot of any of these quantities for the forecast for the valid time. And crucially, we can also use our API layer here to query these forecasts in real time and pull data out over these various open data protocols. So here I'm using the Flux API to query a specific forecast point and pull the data out just as a CSV. So that is incredibly useful if you want to deliver these forecast results to, say, folks who just use spreadsheets. Now, over here, we've got a web map that we've generated where we can take the same forecast and turn it into map tiles that we can interact with and put into any leaflet style, Slippy map, XYZ tile. These are available as soon as our forecasts are committed. And so, in fact, I think this is a good segue back into the slides. What I was starting to describe is how we're actually integrating these results of our forecast with our Flux product. So Flux is our new product which takes data stored in Arraylake and serves it out over OGC standard API protocols. And so this allows us to take the results of those forecasts that we generated and serve map tiles, serve them to spreadsheets, integrate them with other databases, really make them useful the moment they're ready. Okay, so I think this concludes the demo here. I've been running these pipelines all morning, and so we're seeing some fresh data. Oh, yeah, I guess it would be useful to look at the commit log here. So you can see every one of these forecast jobs I run, generates its own commit to my Icechunk store, so I can see exactly what data is coming in when, and I have a full audit history of how my sort of outputs are evolving over time. Okay, so to summarize and start wrapping up, we started this demo building on ECMWF's amazing open source code and models. And we developed a production grade setup on AWS using Earthmover and Coiled. We stored and optimized the initial condition dataset in the Earthmover platform. And that and other performance optimizations we made were able to reduce the runtime and therefore the costs of inference by almost 90%. And we published all of these examples, all this pipeline code in an open source repo for you to check out at the URL provided here. And so these are the type of applications our customers are working with every day. We developed this demo to help them and to help others learn about how to do this efficiently. If you're interested in learning more about the platform, learning more about this demo, and getting started with Earthmover, feel free to just shoot me an email, and we'd love to talk to you and learn more about your use case for cloud native Earth system data and AI weather forecasts. Okay, so I'll leave my summary slides up, and I'll wrap up there, and love to have some time for questions. If Rich says, if we want to try this, we email you. Well, you can just take our code and run with it, so you don't need to email us. If you're interested in using the Earthmover platform to manage your cloud-based data, yes, please give us a call. Roberto asks a very technical question. Did we try to use an ARM cluster? Yes, we tried to use an ARM cluster. It didn't work. That's because EC codes doesn't work on ARM. There's no wheels that work on ARM. So we have stuck with Intel. Yes, thanks, Rich. Got any other questions? Okay. Nishal Karkai, I wonder how much performance gain do we get from virtualization alone instead of rewriting the grid outputs of a ZAR array? It's a great question. We didn't try it. Our mission here was to just simply make this data absolutely as fast as possible. So that involved not just virtualizing, just moving the data over, but also regridding it to the Gaussian grid, and storing it with all variables as part of the same array, so we could just load it in absolutely as fast as possible with as minimal overhead. My guess is that virtualization would maybe get you 20 to 30% of the performance improvements, but the underlying structure of how that grid data is stored is going to provide some limitations on how much you can speed it up. Okay, Sambit asks, is Icechunk compatible with on-premise HPC GPU clusters? Is it open source? So Icechunk is 100% open source, absolutely. It is does work on file systems. However, the advantages of Icechunk are somewhat diminished in that sort of environment. If you have an HPC cluster, you probably already have a way to read data really fast. Those file systems are generally pretty fast. They're shared globally. So, the problem of working with data in object storage is less acute in that sort of traditional HPC environment. So I would encourage you, if you're running inference on an HPC environment, to just start with the files on your file system, and it probably would work fine. The idea here is to help folks do this who don't have an HPC and just use a cloud setup. Okay, Ben asks, how hard would it be to port this to a GCP environment? It would be trivial. I think everything I showed works totally fine in GCP. Coiled supports GCP, Earthmover supports GCP. You just have to change a few lines of config, set things up a little differently. You probably have to figure out which machine type to use in GCP. They don't have the same names as AWS, but everything else would be the same. Someone asked, could I do AIFS on my Mac laptop? Yes, absolutely. Well, actually, no. I don't know the answer to that. I don't know if it will run on a Apple silicon GPU? I would guess not. I would guess it won't work. Okay, is it better to use the output of AI weather models to train other deep learning models, or is it better to fine-tune the original AI weather models for a downstream task? No idea. I can help you run the models fast, but I wouldn't have a strong opinion about that. That's a research question. Will you guys be maintaining the updating the conda environment going forward? No. We are not going to maintain anything in this repo on an ongoing basis. This is a demo, and we have, I think, a pretty clear disclaimer on that at the top. So take this, use it however is useful for you, but this is not a product or a tool that we are planning to maintain in the long term. All right, Lazarus asking, can this run on smaller GPUs as well, or do we need big ones like that? So we systematically experimented to find the smallest and cheapest GPU that we could get AIFS to run on. And so the ones I'm using cost about $2 an hour. So they're certainly not the biggest, most expensive GPUs out there. And so I wasn't able to get it to work on anything smaller. I wasn't able to get it to work on the free Google Colab GPUs. But I think this is a fine compromise, and it feels pretty cost effective to me. Does ECMWF update the weights file, or is that a one-off? So they release so we're using the AIFS 1.0 release. So that's a sort of stable release of this. I presume they will continue to make new releases of AIFS as their technology evolves and the model gets better. So they do update the weights over time. But this version we're using, I believe, is the stable one that has gone into production also at ECMWF. Christian asks, is there any work being done on AI for ocean modeling? Great question, a topic very near and dear to my heart as an oceanographer. Absolutely. Most of that is more in the research as opposed to operational phase, I would say right now. I'm a big fan of the work that the folks at the M² Lines project are doing, led by Lorzana. They've released an ocean emulator called Samudra, which is able to play the role of the ocean in a coupled climate model, but do so much more cheaply than running a full dynamic physical ocean model. And so work is definitely happening there. My impression is that there's a lot of commercial urgency around the weather forecasting problem specifically. We see Google and NVIDIA and Microsoft all investing heavily in that. But, ocean, I mean, we all know how important it is, but it does tend to impact longer timescales. It's by definition a little bit farther from where people live. And so I wouldn't say it's quite as far along in terms of the AI revolution. Okay. I think we can wrap up here. Thanks for everyone for coming by. We really appreciated having all of you